Recording. Perfect. So welcome everybody to the morning session of this beautiful Friday, at least at my place. We're now switching gears, going to different topics, and one of these is the anomalous magnetic moment of the muon. And it's a pleasure to welcome Achim Denig, on measuring the hadronic corrections to the anomalous magnetic moment of the muon. Please.
Okay, thank you, Christian, and thanks to the organizers for the kind invitation to give this talk. So since this is the first talk in a session more or less devoted to G-2, however, I've seen that the program is quite diverse. I decided actually to concentrate in this talk or to give a more general overview of the topic, with some focus on the work we are doing here at MAMI within the A2 collaboration, and especially what we are doing in the BEST3 experiment, the plus and minus collider. So let's start with, okay, no, I cannot change my slides. Sorry for that. Now it should work, yeah. You can see my mouse still, I guess, yeah. Okay, good. So we are dealing with the gyromagnetic factor of the muon. And this is actually, of course, as you know, related to the magnetic moment of the muon. So how actually a muon is coupling to the magnetic field. And in a quantum field theoretical picture, in this Feynman diagram, you see exactly this coupling. And you also know that in Dirac theory, this gyromagnetic factor is actually calculated to be exactly 2. However, you need to take into account in a quantum field theory quantum corrections. And the most relevant quantum correction is shown here. It's actually the coupling of a photon to the muon legs, and that leads to a deviation from 2, and therefore we like to call this problem the G-2 problem. Now, actually, I like to call the anomalous magnetic moment of the muon as the standard model in a nutshell, since we have to take into account all kinds of corrections, and these are not only, as you will see, corrections due to QED, but also due to weak and strong interaction corrections. Now, the goal is here, of course, to compare a precise standard model calculation with the experiment. And I will speak about the standard model, but since not everybody might know the details here, let me show you the great history of this measurement of G-2. This endeavor started actually in the 60s. And in the 60s, it was possible to measure for the first time exactly this quantum correction due to Schwinger, the deviation from 2. You actually insert a muon in a magnetic field, and you measure precisely the spin precession in this magnetic field. Now, in each generation of the experiments, which you see here, the accuracy has been improved. And in each step, higher order corrections, first QED corrections, could be actually resolved by comparing a precise measurement with the prediction within the standard model. The third CERN experiment, the end of the 70s, was for the first time able to actually resolve the hadronic corrections here. And the next generation experiment in Brookhaven was actually constructed in order to resolve the weak interaction contribution. And there the big surprise came, since one has seen a deviation between the full standard model calculation and the experiment. And therefore, it was decided to have a new generation of these experiments at Fermilab. And last year, the first result has been shown. The goal within the next years is actually to improve this standard model accuracy here by a factor of 4. So to a big surprise, about a year ago, the Fermilab experiment did actually confirm Brookhaven. The Brookhaven value shown is here, actually the standard model, the experimental value with the uncertainty here on the right and the standard model prediction here on the left. And actually combining the Fermilab experiment with Brookhaven gives a deviation at the level of 4.2 sigma. And the big question is, of course, now, do we see new physics? Have we resolved not only the weak interaction contribution, but a contribution of physics beyond the standard model? So what we need to do is we need to scrutinize, of course, both the experimental value and the standard model prediction. And actually, nobody has found any issue with the methods which are used in this standard model prediction. Nevertheless, there is an upcoming new experiment in Japan at JPark, which will use a completely different methodology than all the experiments which have done this measurement before. And this is going to be extremely important. Now, as I mentioned, I will speak about the standard model prediction. And of course, the question is, how stable is the standard model prediction? Before I'm going to start to discuss this, let me speculate a little bit, since I like speculations. And let me speculate about the future outcome of the final Fermilab result with a factor 4 improved accuracy. Now, the first assumption is, of course, that the central value will stay constant and the error bar will shrink by a factor of 4. In such a scenario, the deviation between experiment and standard model will be on the level of 5 sigma, exactly 5 sigma, which is, of course, the overall goal to resolve new physics. So it's quite tight. Of course, it could be more on the right, the final result, then we would go beyond 5 sigma, but it could be also on the left. And if you assume in a second scenario that the final result will be here at the left side of this error bar, then we will have only a deviation on the level of 3.9 sigma. The conclusion here is very obvious. We need to improve the standard model prediction. And this is actually a big program in hadron physics, which I'm going to speak about. Okay, so let's look into the numbers. So let's look especially in this uncertainty here of the standard model prediction and the central value. Actually, as you can see, the central value is completely dominated by the QED corrections here. So the final number, which was shown on the previous slot, is this one, and it is very similar to the QED prediction. And that means that the central value is essentially given by QED. However, the electroweak contribution is known much more precisely. And this is due to the fact that these QED predictions have been calculated up to 5 loops. Yeah? So with enormous accuracy. And therefore, the error, the bottleneck in the accuracy of the standard model is entirely given by the hadronic contribution. The hadronic contribution is given by 2 main terms, which is the so-called hadronic vacuum polarization contribution, where you produce a quark loop here. And of course, strong interaction physics is ongoing. It's non-perturbative, and therefore it's complicated and in the regime of hadron physics. The second term is more complicated, is smaller in absolute size, but relatively much less precisely known, is the so-called hadronic light-by-light contribution here, with this coupling of 4 photons to a quark loop. The numbers I show here, about 700 in units of 10 to the minus 10, are actually relatively old calculations by various groups here. And essentially, you can see that the uncertainty of the light-by-light contribution and the vacuum polarization contribution is in the same ballpark, although absolutely this HVP contribution is so much larger here. So I'm going to discuss now in this talk how experiments can actually provide input to this problem here. And before doing so, I would like to introduce a big initiative which started a couple of years ago, which is the G-2 theory initiative. And actually, the goal of this theory initiative is to come up with a theory consensus value for the muon G-2 prior to the upcoming new Fermilab experiment. So therefore, a group of people got together. There were various working groups, collaborations, meetings here, individual smaller meetings, all dealing with the details of this HVP light by light contribution, and lattice QCD also plays a very important role in this initiative. So actually a paper came out about 2 years ago, and this is now the official number for the G-2 standard model prediction, which I'm going to discuss in the following. And let me start with the hadronic vacuum polarization contribution. I have been showing to you the numbers prior to the G-2 theory initiative, which were these numbers here with this uncertainty. And this is now the official number by the theory initiative. As you can see, the uncertainty of 4 × 10⁻⁻10 is actually larger than previous estimates here. So it's, one can say, a conservative number. And the reason is that the various groups which individually calculated this contribution were actually having inconsistencies in the statistical treatment. And therefore, one decided to have a relatively large uncertainty here. So how is it actually done? Now, it is done in a data-driven method, at least in the G-2 theory initiative so far. And it's a method which is well known, which is precise, and which requires input from the hadronic cross-section, from the cross-section E plus E minus into hadrons. Using unitarity, the optical theorem, and analyticity, one can actually use this experimental data, plug it in a dispersion relation, and what one gets out is the contribution of HVP to G-2. You have seen many times this hadronic cross-section here. Actually, there's a kernel function in this dispersion relation which makes low energy contribution extremely important. It's essentially the energy range below 2 GeV, which is relevant here for G-2. Looking into this a little bit more precisely, you see here the budget or the contributions of individual hadronic channels, plus and minus, going into pi plus, pi minus, 3 pions, and so on, to the absolute value and to the uncertainty of this HVP contribution. And you immediately realize that the 2 pion channels, so the channel E plus E minus, going to the rho resonance, going to pi plus, pi minus, is the most important channel. And then follow 3 pions, 4 pions, kaons, and so on. So actually, in the past 20 years or so, a new method came up. This is actually something I discussed in my PhD thesis as a new method, so a long time ago. And this is the so-called initial state radiation method. People like to call it also radiative return. And this is a method which is perfect for the new generation of particle factories, E plus E minus, which were upcoming about 20 years ago, and running at a fixed center of mass energy. So what one does actually is one uses events where one of the beam electrons or positrons radiates a high energetic photon, lowering in such a way the available hadronic mass here, and one gets an energy scan, which was the method so far. So before applied, one gets essentially automatically such an energy scan running at a fixed center of mass energy. So this is successful due to the high luminosity available at the particle factories, but it needs a precise knowledge of the QED corrections here, of course, and this is provided by detailed Monte Carlo generators, especially the Pokhara generator developed by colleagues in Karlsruhe, Kühn, Tschich, and so on. So this method, as I mentioned, started at particle factories, and we actually applied this method for the first time at the Daphne Collider at 1 GeV, getting in such a way access to the Rho resonance. And at the same time, it was also explored at the B factory PEP2 at Babar, where one gets the full energy range, which is relevant under control, of course. And since a couple of years, we are doing these experiments now also at BESS3. So I would like to show you one propaganda plot which shows how nicely this method works. So this is, for instance, the 4-pion channel, plus or minus 2 4-pions. And this was the data prior to applying the initial state radiation technique, large uncertainties, normalization problems of various data sets, large error bars. And now this has been measured by Babar and also by BESS3, preliminary. And you can see here the quality of the data, the fact that one can cover the full energy range in one shot. So it's really a new quality of data which became available here. And this is really a progress. Now, how is the situation for the most relevant channel, E plus, E minus, 2 pi plus, pi minus? This you can see here. These are various experiments measuring this. It's the Rho resonance. You see here the Rho omega interference. So it looks all beautiful. The accuracy of the ISR measurements is below 1%. Also in Novosibirsk, this has been measured very precisely. However, if you look into the details, and this is the relative discrepancy between the various data sets, one observes differences, and differences which are as large as 5% or even more. So obviously there's a problem here. And this problem presently is limiting our knowledge of the HVP contribution for G-2. So I promised that I'm going to speak a little bit about BESS3. At BESS3, we have done this measurement a couple of years ago. We actually found an issue in our covariance matrix, which reduced the uncertainty, statistical uncertainty, and we came up with a new publication last year. And you see here the BESS3 uncertainty, which is with 0.9% systematic accuracy, not yet competitive or really competitive to the high accuracy analysis of CLOE. This is actually a combination of 3 CLOE measurements and of the Babar measurement from SLAC. And presently, we are intensively working on a new analysis using higher statistics, much higher statistics than our previous analysis. And our goal is to reduce the uncertainty down to 0.5%. And this we will do by doing a so-called untagged analysis in which we actually we are doing this by performing a tagged analysis where we still measure the initial state radiation photon in the detector as we did before. So we tag the photon and we tag the hadronic system, but we normalize to the production of 2 muons. And as a matter of fact, like this, the limiting factors in our table of uncertainties before, namely the luminosity and the radiator function, drop since they appear in the nominator and denominator. And this gives the basis to a significantly reduced systematic uncertainty. In the meantime, we are also working on an untagged analysis in which we do not require the photon. And this is actually comes with the high statistics for these kind of events. And we already now, with the existing data, we can significantly improve over the only available data set from Babar. So stay tuned for news from BESS3 regarding this channel. I also would like to mention a new inclusive R measurement, which was published this year. And this is actually relevant for G-2, but first of all to the running of the electromagnetic fine structure constant at the Z pole, and therefore it's very important for electroweak precision physics. This is essentially also one of these R measurements where one normalizes to the 2 muon yield. One needs to take into account, of course, the luminosity, reduced background, need to take into account radiative corrections. But what one needs, first of all, is actually good knowledge of the efficiency of the event selection, and therefore a Monte Carlo generator is needed. And a lot of work has gone exactly in the generators. We have actually developed 2 Monte Carlo generators. One, Lund area law, which is purely based on theory, and a so-called hybrid generator, in which we combine the high accuracy Pokhara Monte Carlo generator with a generator based on existing data sets, for instance, from the huge program existing at Babar and also in Novosibirsk for these cross-section measurements. And indeed, these 2 generators came out to be in agreement with each other, and therefore we get an overall error below 3% for this inclusive R measurement. Here in red, you see the new best 3 data. And surprisingly, we find a systematic deviation from perturbative QCD and also from a previous scatter experiment up to some extent. And we will see what will be the impact of this new data on the running of the electromagnetic fine structure constant. Okay, so let me conclude for the first part, actually the main part of my talk, which is the hadronic vacuum polarization. I've shown to you that we have to measure this 2 pion channel precisely. Presently, there's a discrepancy between the most precise data sets from Chloe and Babar. And luckily, new facilities will provide new data. There's an update of Babar. BEST 3 will do this measurement. Novosibirsk will do this measurement in a classical energy scan. But also BEL 2 will be doing this with the large statistics which will be available. I've mentioned the new inclusive R measurements, which are also very important. And thinking optimistically, and assuming that once this 2 pion channel will get under control, there's actually a reduction of a factor of 2 in positively thinking might be in the next couple of years be possible, which will be very important for G-2. This is actually a plot from the theory initiative. Here you see the HVP number I've been showing, previous dispersive estimates here. And in blue, you see lattice data. And up to last year, the accuracy of lattice was not yet competitive with the dispersive approach. However, there's now a new result from the BMW collaboration, which is actually significantly smaller than the dispersive approach and appears to be almost not in conflict with the standard model anymore. This is actually the basis for hours of discussion, and my proposal is to defer this to the discussion session later this afternoon. Okay, in the last couple of minutes, I move on to the hadronic light-by-light contribution. Again, I show here the value which was agreed upon in the G-2 theory initiative. So actually, compared to previous estimates, there's a significant reduction of the uncertainty. And actually, I will show why this is the case. And the reason I can tell you already now is because also here now a data-driven approach has been applied, while previous estimates, this is again the status like 2 years ago or so, all the estimates were model dependent. Essentially, what one knows is that one has to decompose this hadronic bubble here in terms of individual contributions, pion exchange contributions, loop contributions, contributions due to scalars, axial tensor resonances. And if you look at the individual contributions, you realize that the pseudoscalar contribution here is by far the dominating effect, with a large uncertainty here. Now,
5 minutes,
what? Sorry?
5 minutes.
Okay, thank you. I will be done in 5 minutes. Yeah. What actually is the progress now due to the G-2 theory initiative is that one changes from assuming these estimates, these contributions here in models, to a data-driven dispersive approach. And if one looks, for instance, in the most important contribution, which certainly is the pseudoscalar contributions, one can relate actually this graph here to transition form factors. And transition form factors can be measured in a plus and minus. They can be measured at low Q-square, at low momentum transfer, also by means of Dalitz decays, what we do at MAMI, for instance, and it's done elsewhere. However, the problem is that really what is needed in this dispersive approach is a double virtual transition form factor, where both photons here are virtual. And the problem is that presently we don't have data for these transition form factors. So actually what one uses for the time being are lattice QCD calculations or dispersive analysis of exactly these transition form factors, the double virtual transition form factors. And the big program for experiment is now to measure for the time being the single virtual transition form factors and compare with exactly these lattice calculations and dispersive analysis. And later on, with upcoming new data, also for the first time to come up with the double virtual transition form factors. So the first step we are doing right now quite successfully at BEST3, and we are doing exactly these transition form factors in a plus and minus. The method is quite simple. You scatter an electron and a positron, and one exploits these gamma-gamma fusion processes, which produce pseudoscalar mesons, 2 pions, and so on and so forth. So actually, the virtualities at BEST3, this is a famous formula, which you know from electron-proton scattering, are such that at the kinematics at BEST3, one can measure the kinematic range, which is really relevant here for G-2 for the hadronic light by light contribution.